Oh, come on. How's it going? My sound working okay today? Can you hear me? Okay, cool. Both of the cats are awake and in this room, so hopefully they won't interrupt too much. Everyone having a kind of reasonable week, at least? It's good that it's going all right. Slow is probably good, right? I don't know. It's better than having 5,000 things at once. Slow every day. Yes, that's the paradox of 2020 is the days feel very slow and then you blink and it's 3 months later. I can't believe we're at the end of October. At least it's finally starting to feel like fall. Not be 100 degrees. Still pretty, I guess, yeah, it's still pretty hot there. Hopefully it'll cool down soon. It's actually, there's a chance of rain in Northridge on Sunday, which is, gosh, I hope it does. We need that. You'd rather have it super hot than super cold. Yeah, I mean, that's definitely, I mean, I prefer neither. But my feelings are it's easier to warm up when you're cold than to cool down when you're hot, I think, but different people are adjusted to different things better. I mean, ideally, like it would be 65 all the time. That would be perfect for me. Anyway, oh wait, no, we've got a few more seconds. Oh, are you're from Cuba? Are you in Cuba right now? I don't think I've ever had a student be, oh, okay. I was gonna say, I don't think I've ever had a student actively be out of the country in my class before. Oh, you're in LA, okay. Anyway, it's now 2, so let's get started. So last time we started with going over stuff about the last test and then got into sedimentary rocks. And so just want to remind you that like if you want to go over the test with me at any point, just you can come to my office hours on Zoom. So nobody came yesterday. It was just me sitting alone at my computer. But yeah, Tuesdays from 2 to 4 are my regular Zoom office hours. And if that doesn't work, but you still want to go over the test or you just want to ask me about a topic, anything in the class, just you can make appointments with me. I'm happy to do that. Don't forget there's now an extra credit posted that'll be due right after our next test. So if you're interested in getting some extra points, I would definitely go ahead and do that. Also, last time we talked about the idea of kind of having a discussion forum for the class. And so what I've done is set up some stuff on the discussions section of Canvas. And so if you go on the, I should be showing that probably, but if you go on the left side of the Canvas thing, when there's that whole column of links, there's one that says discussions. And if you click on that, it should now show you a few little discussion forums. They're not graded, they're not worth points. You don't have to use them at all. But if you want to, right now I posted 3 sub discussions. So there's one on actual real world geology. So you can ask things about the class. You can talk about stuff you're not sure about. You can, if you find a cool rock, ask about that. If you're curious about a landscape, ask about that. Then there's a second one for geology in the media. So that's all your geology in fiction. That's where you can talk about Avatar. It's where you can talk about anything where there's fictional, either geologists or earth powers. But also, like, if you see like the news talking about something geological and you kind of want to talk about how they're portraying that, you can put that in there too. And then I put a show us your pets section, so you can post pictures of your animals, or if you find some other good animal video or picture, even if it's not yours, you put that there too. So hopefully you can all see that if you give it a look. If not, I guess let me know and I'll see what I can do. But again, that's just there if you want to use it. It's not mandatory at all. And if you all think of any other kind of subheaders for that discussion board that you would like to see on there, just let me know. So does anyone have any questions or concerns or just general anything before we get back into rocks? All right, then let's get back into rocks. And if you do think of anything later, just let me know or put it in the chat or whatever. But anyway, last time we introduced sedimentary rocks and we talked about where sediment comes from. We talked about how sediment or clasts comes from chunks of other rocks. And we talked about this 5-step process for how stuff goes from being sediment to being a rock. And so I'm actually going to advance a slide first and then move back. So we talked about this 5-step process of weathering, which is when the source rock breaks down into different clasts. Erosion, when those clasts detach from the source rock. So that's a distinction that, like, weathering and erosion, it's very, very common to think of them as the same thing, and don't worry about it if that's what you thought. But they are different in that weathering is just the breakdown of the rock and erosion is actually detachment. Then transportation is when the clasts get moved to a no place. Deposition is when they get dropped off. And lithification is then when they stick back together into rock. And so last time we spent a while talking about weathering and about the different kinds of weathering. And so broadly, you can have physical weathering, which is just beating the crap out of the rock. It's just literally breaking it with force. And then we talked about chemical weathering, which is chemical reactions that break down a rock. And those were, if you remember back when we were talking about minerals, like, which seems like months and months ago now, the things that do chemical weathering, a lot of them are basically the same things that just break down minerals in and of themselves. So when I say, like, this class isn't, like, the tests aren't cumulative, but stuff comes back, that's kind of the kind of thing I'm talking about. And so before we move on, so I have erosion highlighted here, but I've got one more thing I want to say about weathering before we move on to erosion. And that was, even though I introduced those things separately, even though I talked about physical weathering and chemical weathering being different processes, and they really are, they have very different mechanisms, but usually where you get one, you get the other. So, like, let's say you have an intact piece of granite, like here's a piece of granite that says it's intact. And this is a figure from your book, by the way. If it starts to chemically weather, then that makes it easier to crack it. So, like, once the chemical weathering starts destroying the minerals in that rock or turning them into weaker minerals, then it's much easier for you to break that rock with a hammer, or for a tree to crack it in half, or for there to be spaces where like ice or salt can get in there and wedge it apart. But on the other hand, like let's say you start with a rock that first is solid and then you crack it in half with a hammer or a tree root or a piece of ice or whatever. Then you actually have more exposed surface area. And where you have more exposed surface area, there's actually more places where chemical reactions can take place. So these things kind of go hand in hand. Where you have a crack in the rock, a physical crack in the rock, the chemical reactions will get in there and start weakening the rock further. Or where you have a chemically weakened rock, it will be easier to crack it and break it apart. So separate mechanisms, but they work together to break down rock over time into sediment. So any questions about that or about any of the stuff we went over last time before we move on? So I guess we're gonna move on. All right. So I apologize in advance for today that there are a lot of slides that are just words, and some of it is because a lot of these processes are something that they're slow enough or on a scale that's hard to get a picture of them. So today is going to be a lot of words, but then next time we're going to see a whole lot of pictures, because today we're going to go through the rest of this process and just general classification of clastic sedimentary rocks. But then next time we're going to talk more about specific ones and the situations they form in. So there will be a lot of pictures next time. Let me advance the slide. Okay. So anyway, weathering, we're breaking stuff down. But now we're getting in, now let's talk about erosion, where the stuff that has weakened and broken down and cracked and undergone chemical reactions actually detaches from its source rock. And so let me ask you, what do you think are some ways that could happen? What could detach these things? You can either say it or type it.
I want to say like the wind.
Yeah. So yeah, go ahead. Sorry.
Yeah, no, just like the wind and like maybe ice can like.
Yeah. So wind, ice, absolutely. Animals can totally take things. So can plants. Earthquakes and landslides, definitely. Although earthquakes and landslides sort of automatically go straight from that into transportation, mudslides as well. And so actually next Wednesday, we're going to talk about landslides and mudslides a lot. But yeah, wind, water, living things, ice, just gravity. Like if you just shake a rock enough in an earthquake that these things fall off, gravity. Again, a landslide is kind of many of the steps at once, but we'll get there. I mean, it's still right. It just also goes further than that. So for now, we're gonna focus on the ones that are just the erosion step, and I'm really happy that you basically got them all. But I'm gonna go into a little bit more detail on them. So there are a few erosion mechanisms. These first four up here involve a fluid. And so a fluid could be water or it could be air. A fluid is just something that flows. And so these first four, well, actually, I guess the first one is also something that can be done by animals or plants. So plucking is literally like you're taking it. It's just like plucking a feather or plucking a flower. They're just being taken. They're being pulled, sometimes by animals, sometimes by actually plants working their roots in. Sometimes even ice can do that, but it's basically that actively just pulling things out. The salt wedging does that. And that could also be that option of you going, huh, that's a cool rock. I'm gonna touch it. Oh my gosh, I just pulled part of it off. That would count for that too. So does that one make sense? So the next two are more easy to confuse with each other. So abrasion and scouring are both pretty similar. And the difference is just both of them are just scraping clasts off the source. But abrasion would be kind of like if you were using sandpaper. So something is getting scraped with something else rough. So just like if you're taught sandpaper would be in the abrasives section of the hardware store, or like if you're buying a rough sponge to clean sticky stuff off your dishes, you're using an abrasive to clean stuff off. So it's that idea of something rough to get rid of the other rough stuff and polish it and remove it. Whereas scouring is the idea, it's kind of like using, like a sand blaster or like a high pressure water thing. It would be kind of like if you, let's say, rather than wanting to wipe your dishes, you just sprayed them with the highest water pressure you could to just try and shove all the dirt off. That would kind of be what scouring is. So abrasion still generally happens. It can be a rock scraping past another rock, like you would have in an earthquake or sometimes in a landslide. It can also be that, like, let's say you have a really windy day and there's a bunch of sand suspended in that wind. That sand would be scraping stuff off the rock as it's blowing in the air past the source rock. Does that make sense?
Did you say that one was abrasion? Or...
Yeah.
Oh, okay.
So when you're using something rough to scrape something off.
Okay.
Have any of you ever been outside in have you been at the beach at a windstorm? Have any of you?
I do not believe I have.
I don't recommend it. So back when I was a kid and my family so I'm originally from the East Coast, and my family went to the beach in Delaware, and there was a tropical storm. And the previous year there'd been a tropical storm that we evacuated from and then didn't need to. And so this time they were like, no, we're not going to evacuate. That was stupid. And then it totally came. And then because we were dumb, we were like, let's go see what this looks like. And so when sand is blasting past you at like 65 miles an hour, it hurts. It will scrape the skin. It's like you skinned yourself without actually falling and scraping it. It hurts real bad. So abrasion, so apologies for the potential thought of pain, but basically abrasion is that kind of thing happening to a rock rather than to you. So don't go to the beach in a windstorm or a tropical storm. Don't do it. What? Sorry.
I said noted.
Any questions about abrasion? Meanwhile, scouring, again, is just like, imagine you were, let's say you get back from a trip and your car's real dirty and you just turn the hose on the car. You're just kind of blasting stuff off with water, basically. It's like those high pressure jets at the car wash are scouring the dirt off your car. So in this case, the scouring could just be really fast wind or fast water without other stuff in it. In reality, most of the time when you have one of these things happening, you're gonna have the other. Usually you're gonna have some combination of abrasion and scouring. But the difference is that in abrasion, it's stuff suspended in the wind or water that's doing the scraping, or sometimes it's ice doing the scraping. And in scouring, it's just the water or wind itself. So do those make sense? Do you understand the difference? Cool. Then the next one that requires, in this case, water is dissolution. And so this is one we already went over. We went over this when we talked about how minerals get destroyed and also about chemical weathering. So this is kind of a step where it's actually kind of both chemical weathering and erosion. They do kind of overlap. But in this case, if the water is just sitting on the rock and chemically breaks down the minerals and just hangs out, it's weathering. But if that water is flowing past the rock as it's destroying the minerals, and actually, or as it's dissolving the minerals, and then the dissolved stuff, rather than just hanging out on that rock, gets pulled away as the water flows, then it's erosion rather than weathering. So it's a fine line, and I honestly wouldn't worry about it too much. But does that make sense? Cool. And then the last one, falling, it's exactly what it sounds like. Stuff falls off. If it gets loose enough, it falls. If it's at a weird enough angle, it falls. Sometimes if there's an earthquake, it falls. I feel like I don't need to explain that anymore. Hopefully not. Sometimes erosion can be, sometimes falling can be like a massive boulder falling off a cliff. Sometimes it can be a single grain of quartz, like just losing its attachment to a piece of granite and just plunking down on the ground. So the scale of all of these can range from very small to very large. But do all of these make sense? Does anyone have any questions about them? Cool. Then let's keep going along the line for our sedimentary rock creation. Let's move on to step 3. So transportation is your moving stuff. Classes can get moved to a new location. And so now I'm going to ask you again, what do you think can do that? What can move these clasts now that they've detached? Wind, exactly.
Earthquakes and mudslides?
So again, earthquakes and mudslides are, so glaciers, absolutely. Mudslides, absolutely. Earthquakes, not so much, because an earthquake is probably, it's gonna knock stuff down, but it's not necessarily going to pull it to a different location. It's just gonna fall and like end up there. But yeah, wind, glaciers, rain, air in general, heavy rain, water in general, rivers, glaciers, yes, gravity too. But I guess in gravity, you know, earthquakes are rarely part of the sedimentary process. You can kind of shoehorn them into most of these, but we're gonna actually talk about earthquakes during our metamorphic rocks section, because the effects that earthquakes have on rocks, it can do some pretty crazy metamorphic stuff. But yeah, all of these things you said in the chat are spot on. But the 4 major categories we're going to break this down into are wind, water, gravity, and ice. These are the big 4. Hopefully you said them. So hopefully it's intuitive. It did seem intuitive. But each of these kind of has a different level of what it can transport, both the size of the things it can carry and the distance it can carry them. So like wind can only carry pretty small stuff. But I mean, you've seen that in action just recently. Like just think about the fires and how like, even if you didn't necessarily live in Pasadena during the Bobcat fire, those pieces of ash got carried pretty far from that fire. Or just think about whenever there's Santa Ana winds in the fall and the air gets super, super dusty. All of that are very, very tiny clasts that are being carried in the air. And depending on how hard the wind is blowing, it can actually carry them pretty far. So you can have wind-related stuff end up miles and miles and miles from the source, but all of it's going to be pretty small. Because no matter how strong the wind, even thinking about that hurricane, like it can probably pick up, like, I mean, they can maybe pick up trees, but they're generally not gonna like pick up a boulder and launch it at you. And good thing. I mean, imagine how difficult life would be if the wind could carry boulders. It would be pretty. Basically, engineering would have to be a completely different field if the wind could carry hard mode. Yeah, no kidding, quite literally. So wind does not carry boulders, but it can carry sand, it can carry dust, it can carry silt, it can carry small stuff pretty far. But these other 3, water, gravity, and ice, can carry some pretty big stuff. So water, as it turns out, even only like 6 inches of flowing water can pick up your car. Water is not something you mess with. Water can win at like everything. But ultimately the size of the class that it carry depends on, well, first on how much water there is, and second, how fast it's flowing. So like if you have something, like even if you have a huge amount of water, like say you have Lake Michigan isn't going to carry a boulder because it's not really flowing very fast. It's not really flowing, it's a lake. You do get very specific sedimentary rocks in lakes versus in rivers. That's something we'll talk about next time. But yeah, if that water's just hanging out, no matter how much of it there is, 100% of people who drank water have died. Yeah, you can't really argue with that. But yeah, if the water is flowing really fast, it can carry some big stuff. And actually, again, you can have even just like 6 inches deep of water. And if it's flowing at like whitewater rapid speeds, it can carry some really big rocks. And so that's something we're going to talk about in a lot more detail when we talk about rivers and floods next Monday. No, a week from Monday. November 2nd is when we're going to talk about that. And so there's a reason that I grouped the rivers and floods with sedimentary rocks, is because that moves some pretty big stuff. And then also, depending on how fast the water is going and how much water there is, it can carry that stuff pretty far. And so even if it doesn't necessarily carry the really big rocks really far, it can still carry small stuff quite a long distance. So thinking of something like the Mississippi River, like it doesn't necessarily go very fast most of the time, but it can carry sand from all the way up near its origin in Minnesota, all the way down to Louisiana. So water is powerful, and what exactly it does just depends on how much and how fast it's going. Meanwhile, gravity, I mean, gravity is always the same speed. Gravity is goes at a rate of 9.8 meters per second, where is the acceleration due to gravity. That's always what it is. So if something falls, it's going to fall at that speed, no matter how large it is. We do also group rolling in this category. Like if something just gets nudged down a hill and it keeps rolling, that will go into that category. And honestly, just the distance that it goes just depends on how big the cliff, how far the fall, how long the slope. You can have gravity move something 3 inches. You can have gravity move something 3 miles. It just depends on the specific conditions. But when we talk about landslides, which is a week from today, that's all about gravity in action with sedimentary rocks. And so that's both gravity doing transportation, and then also, as it turns out, some other sedimentary features can make it easier for gravity to transport things. So it's kind of a give and take there. But yeah, gravity, I mean, you can have a massive, massive boulder fall in gravity. You can have an entire chunk of a mountainside fall off. But it can also be, again, a teeny tiny little rock. And then the last one, so we list ice separately from water, because even though it's just frozen water, even though ice is water in mineral form, even though ice is just water in mineral form, it behaves in very different ways, because rather than being a rapidly moving, flowing thing that can grab every piece of whatever is in its way, ice is a solid, and so it acts as a force, as a real pushing thing. It's not going to pick stuff up necessarily, but it's going to drag what's under it. And it's also, if something falls on top of it, it can move that really far. So ice can grab some absolutely just ginormous rocks. Like if gravity knocks over a boulder and it falls on that ice, if that ice is moving, if that glacier is moving, it can carry those boulders for miles and miles. Yeah, my cat is, I don't want to encourage her while I'm lecturing. I can grab her at the end again if you'd like. I just had to get her from behind the computer because she has stepped on the power switch, and that would be bad. But anyway, so glaciers are a massive sedimentary force, and the distance they carry stuff just depends on how far the glaciers can extend at that time. So in that way, it's actually very climate dependent. I mean, honestly, most of these are, I mean, gravity isn't climate dependent, but the amount of wind and water you get are also climate dependent. But glaciers in particular are, because they'll only go as far as ice can stay solid. So you get a lot more glacial related transportation in colder climate. But have any of you ever been out to either are any of you rock climbers? Has anyone ever been out to the Buttermilk Boulders in the Eastern Sierra? Well, I'll show you some pictures of those when we talk about, you wish you'd been out there. It's actually not super far. But yeah, I'll show you some pictures of those when we talk about glaciers, which I think is a few weeks from now. But glaciers move these really gigantic rocks many, many miles from the top of the Sierra Nevada down to the valley floor. But so yeah, glaciers are, I mean, that sounds scary, but they're slow. Honestly, I would say the one that's the scariest here is the water. Because gravity, like usually you're going to get some indication that something's about to fall and you can get out of the way. But water is just, water's going to kick your ass. Water wins. But anyway, any questions about any of these mechanisms? These are things we'll come back to again and again as we talk about, well, I mean, as we talk about rivers, as we talk about landslides, as we talk about glaciers. And then also as we talk about the specific environments where different rocks form. But any questions about these as transportation mechanisms? Cool. All right. So then let's keep going down the line. So next thing is deposition. It's eventually the transportation is going to stop. Eventually the rocks are going to get off the bus. And so deposition is the process by which clasts get dropped off. And so thinking about our transportation mechanisms, thinking about what we just said, what do you think causes clasts to be deposited?
The same things that transported them.
So yeah, the same things that are transporting them will deposit them, but like what causes them to stop being transported?
Oh,
So I see landslides. Yeah, certainly when the slide is over, it stops when it runs out of energy. But what do you think would cause something to stop being carried by all of the stuff? So yeah, sinkholes are a gravity kind of situation. Sinkholes, we'll talk about a little bit when we talk about landslides, but yeah, once it hits the bottom. So the riverbank, so riverbanks are made up of rocks that stopped being carried by the water. So yeah, drought is another thing. It means there's less water. But let's think about that question of the riverbank. So what might cause the rock to stop being carried by the water?
maybe clumping together with other sedimentary rocks and like gaining weight.
So the clumping together happens after the deposition, but the
Okay.
weight is a really important concept there. So think about a stream. Like let's say you've got a river and it's carrying some rocks. What do you think might cause that river to drop the rock?
It stops moving.
Yeah, so if the water slows down or stops, yeah, it's not going to be able to carry stuff anymore, right? So the faster the river is moving, the bigger stuff it can carry. So if it slows down, it's going to start dropping the heavier stuff. And so usually rivers are actually slower at their edges than they are at the middle, which we'll talk about why next week or on the 2nd. That's when we're talking about rivers. But the slower parts are usually on the edges. And so those heavier rocks are going to get deposited as riverbanks. But yeah, basically for anything that's flowing, if it stops or slows down, it's going to drop what it was carrying. So yeah. So the deposition mechanisms, if the wind is carrying it, if the wind stops blowing, it's going to fall. Water, if the flow speed slows down or stops, stuff's going to fall. So if it just slows down but doesn't stop, the bigger clasts, the heavier clasts are going to sink and stay where they were, and the lighter, smaller ones are going to keep going. So that's why you'll often find different things at different places along a river. Like you'll find bigger rocks along a steeper river because it's flowing faster than you will along a river flowing on a very gentle slope. And we'll talk a lot more about that on the 2nd. But basically the speed matters here. With gravity, it's just the rock stops when it hits the ground. Like it's not going to fall through the ground. It's going to stop. And then with ice, there's kind of a couple of things here because glaciers are basically frozen rivers. And we'll talk, again, we've got a whole lecture about glaciers coming up on the 5th. whenever that next class is. We have got a whole glacier lecture coming up. Maybe it's the 3rd that's our rivers lecture, whatever, it's on the schedule. But with glaciers, with ice, there's kind of two steps. One is that if it advances or retreats past the place where it was dragging stuff and there's no more stuff that it's going to drag, like if it goes beyond where they were, it's just going to keep going. Like if it retreats past what it was dragging, like if it, just advances back up the mountain, because glaciers can actually go both uphill and downhill, unlike water. If it just goes past the stuff it was dragging, it's just going to leave it there. But the bigger mechanism with glaciers is that, remember how I said very often gravity will knock stuff over onto them, or things will fall onto them? Or sometimes as they're freezing, rocks will end up in there. Is basically when a glacier melts, it's going to drop what was on top of it or inside of it. Because as soon as it's liquid water, even at its fastest, can't carry stuff as large as what a glacier can carry. But usually melt is very slow. It's usually not the speed of like a river. So melting of a glacier is just going to cause those things to fall down in place. So does all of that make sense? So any questions about deposition? So you'll notice that this is a sequence of events that leads to the formation of sedimentary rocks, but it's also kind of a logical sequence of if this one force erodes the rock, it's probably also going to transport the clast, and then the same thing that transported it has to deposit it. So you kind of end up with different classes of sedimentary rocks depending on which mechanism was at play here. Was it wind? Was it water? Was it ice? Was it gravity? You're going to end up with some different stuff just because you have a different sequence of going from erosion to transportation to deposition with each of these mechanisms. So that's why this is a really good one to just think about it logically. Like let's say you can't necessarily remember exactly what ice does to a rock. If you just think about the properties of ice, like it's solid and you can put stuff on it and it's gonna not hold things anymore if it melts. So a lot of these are just, if you think logically about how wind and water and gravity and ice work, you can probably work through these steps of going from erosion to transportation to deposition. Because those 3 steps they're pretty much always related to each other. Weathering might not necessarily be related to the same process that does the erosion, transportation, and deposition. And our last step, lithification, kind of works the same way, regardless of the other 3 steps. But those 3 are pretty much always going to be related and always be tied to whatever force is at work. So does that make sense? Does that sound good? Cool. Okay, so then let's move on to the last step, which is lithification. So far, these first 4 steps we're not really working with, you're working with clasts rather than rock. You're working with small pieces of a source rock. But until then, these things are still kind of retaining the properties of their source rock, although they're getting modified as they are transported and deposited. And that's something we'll talk about a little later today, is these processes don't just take things as exactly as they were when they were eroded. The clasts will actually change depending on how they're being transported and deposited. But once we have lithification, that's just all of this stuff is turning back into a new rock that's going to be very different in properties from its source rock. I mean, I guess you could weather away a sedimentary rock and have it turn into a different sedimentary rock. You can totally have that happen. But the second sediment, even in that case, though, the rock that forms from lithification is going to have different characteristics from the original rock that weathered, just because all of these steps change things as they move. But lithification, that's sticking back together, it has 2 steps. So one is compaction, that's squishing, and one is cementation, which is sticking. So in a little more detail, again, lithos is Greek for rock. Lithification means to become rock. But this is specifically a term that's used for sedimentary rocks. Like you wouldn't say that for a metamorphic or an igneous rock, because in an igneous rock, it's cooling. And a metamorphic rock, it was already a rock to begin with. You're just turning it into a different kind of rock. But in sedimentary rock, it's lithification, where you're turning sediment back into rock. And so the two steps are compaction, where things are getting, the clasts are, they pile up in whatever setting where they were deposited. And as more and more stuff piles on top of them, they get squished together under the weight of the other clasts, and they become more densely packed. So like here, if you imagine, you've got your pile of papers on a desk, like the stuff, even though they're all the same size, these pieces of paper, it's going to be way easier to take a piece of paper from the top of this pile than it is from the bottom, because the ones on the bottom, even though they're the same size, even though they're the same weight, because they're under the weight of all of that other stuff, it's going to be a lot harder to pull that piece of paper out from the bottom. So does that make sense? And so in some cases, depending on what those clasts are, that might be enough to really make them pretty solid. But usually you need one last step to glue everything together. And so in this case, usually where you have sedimentary rocks, you usually have water nearby, or sometimes it's wind. But usually you're going to have some sort of water flow by the time it gets deep enough into the ground where this is happening. Because this lithification process doesn't necessarily happen right on the surface. You're always going to have a layer of just sediment or just soil before you get into the place where you get lithification. It's always below the surface. It's nowhere near as deep as like where igneous rocks, like where intrusive igneous rocks form, but it is below the surface. And so it's usually at a point where even in dry climates, there's still some groundwater. And where you have groundwater just trickling through the earth, you're also going to have minerals in that. Like groundwater is usually not pure water. It usually has particles of dissolved minerals in them. And basically, as that groundwater flows through these clasts, the minerals in it are going to precipitate out of a solution and stick those clasts together. So like if you remember when we were talking about how minerals form, and I gave you that example of like rock candy, where you stick a string or a stick into a solution full of sugar and sugar crystals form on the stick. This is very much the same idea, except the mineral crystals are forming on the clasts rather than on a stick. And so in this case, if enough of that happens and it just starts to fill in all of the remaining gaps between the clasts and really welds them together into a new rock. And so like if you think about just actual like construction cement, you have little particles of rock suspended in a more liquid thing. And it's used to stick things together. This is kind of the same idea, just naturally. And so here the picture I put is like, imagine, you spill your coffee on your papers, suddenly they're going to be stickier. It's going to be harder to pull them apart because adding this new substance to the situation makes them stickier and changes the properties. So it's kind of that same idea is clasts that were just jammed together get cemented together as with the addition of minerals that are suspended in a fluid. So does that make sense? And so if you remember our definition of a sedimentary rock, where it's minerals that are cemented together, where you usually have clasts that are cemented together by a cement is the word we use. So the compaction is how the clasts get near to each other, and the cementation is how they get stuck together. And generally, the smaller your clasts, the less cement there is, just because there's less space between them. So it's easier to stick them together. But when you have really big clasts, like that example of a riverbank from earlier, you might end up with some pretty big rocks on a riverbank. And eventually they're going to still get buried enough to become sedimentary rocks that have those riverbank rocks and also a cement around them. And so in that case, when you have bigger clasts, you're going to see more cement around them. So in something like a sandstone, you might barely see the cement. But in other things, you might go, well, that's a fine-grained rock with bigger chunks in it. But does this all make sense? Are there any questions about lithification and compaction and cementation? Cool. So now we have made a sedimentary rock, or I guess the elements have made a sedimentary rock, where you go from, again, weathering to erosion to transportation to deposition to lithification. And that ends up with a clastic sedimentary rock. And so from here, we're actually going to talk about how clastic rocks are classified. So we're going to spend the rest of today on that. Then Monday, we're going to talk about how clastic rocks form in different environments, but how environment affects rock formation. And then we're going to also talk about the other 3 kinds of sedimentary rocks next time, because those are a lot. There are only so many ways those can form.
Professor, do you think you can explain weathering again? Just like a quick abbreviation.
So yeah, so weathering is when the source rock breaks down. So when it becomes structurally weakened in a way that it can come apart, but it doesn't necessarily actually come apart until it erodes. Does that answer your question?
Yeah, it does. It does. Thank you.
Yeah, so, and the way that all of these things happen and the different environments in which all of them happen strongly affect the kind of rock you end up with. So, yeah. But basically, in identifying the kinds of clastic rocks, it's going to be a totally different kind of ID from igneous rocks. Igneous rocks were all about what minerals were in them. We're all about just what's in it and how did it cool. But in sedimentary rocks, I mean, there's certainly some degree of mineral stuff in it, but like that doesn't matter that much. I mean, that's just a way of like, you can have sandstone in general, but you can have different subsets of sandstone depending on what minerals the sand is made out of. So in the context of our discussion, we're actually not going to talk a lot about minerals here in terms of the composition. I mean, all of these rocks are made of minerals by definition, but we're not going to talk too much about like what is in them. We're going to care a lot more about the structure of that rock and what it tells us about the process by which it formed and the environment in which it formed. But these 5 things that we use to classify clastic rocks are just how big are the clasts? How big are the chunks? Are they little? Are they big? How much cement is between them? And then there is that just what are the clasts? What minerals are they? What kind of rock did they come from? That can tell you about the source, but again, we're not going to really focus on that one in this class. Then angularity and sphericity, though, that's a big one. And that's basically angle or sphere. Is it rounded or is it pointy? Because as it turns out, that can tell you a lot about especially the transportation process. And we're going to go through most of these on individual slides in a second. So like, don't worry about it too much right now. But yeah, it's how rounded or how angular. And then sorting is basically, are the clasts mostly the same or is it a mix of different stuff? Like, are they all mostly the same size, mostly the same shape, mostly the same mineral, or is it a mix of totally different stuff? Because that can tell you a lot about, especially about deposition, but also transportation. And then the last one is the character of the cement. So character is the term they use for it, but it basically means how much of it is there and what is it made out of? Is it more silicon rich or is it more calcium rich? Because those are the 2 main ones that you're going to find in sedimentary settings. Basically, if you were given a sedimentary rock, these are the things you'd look at. And then the last slide we're going to see today is kind of a table that you can use for going, okay, if it's this, this, and this, it must be this kind of rock. If it's that, that, and that, it must be that kind of rock. But before I go on to each of these things, or most of these things individually, I'm not going to spend more time on class composition or cement character. But does anyone have any questions about this before I move on? let's talk about clast size. So it's really just how big are the chunks? Is it a large boulder the size of a small boulder, or what else is it? So did any of you remember, did any of you see this tweet back at the beginning of this year? This was all over Twitter. Maybe it was just all over geology Twitter. I don't know, but it was all over Twitter for a few days. And this is just like peak comedy to me. It's a large boulder the size of a small boulder. It's completely blocking. Yeah, it's one of those, you have to think about it for a second. It's like a large boulder the size of a what? And so it turns out the person who wrote this tweet meant to say a large boulder the size of a small car. But she said a large boulder the size of a small boulder. And now if you look at their Twitter, like, she's totally embracing all the rock puns. But a boulder is actually a very, very large category. And technically, you could look at this boulder and go, yeah, that's a rock. And a boulder is like a whole rock. Like you could go, yeah, that's a boulder of granite. That's a boulder of sandstone. That's a boulder of schist. Schist is a kind of rock that's spelled. That's a metamorphic rock we'll talk about later. But a boulder, so you can have a situation where like a clast is also an entire rock. So in this case, like you would totally call that an entire rock. You would call it a boulder. But a boulder can be just anything that's more than 256 millimeters. So 25 centimeters, it's basically like a foot. Actually, give me a second. I'm going to grab a ruler. Should have done this before class. Okay, so here's a ruler. It has metric. So 256 millimeters is 25.6 centimeters. So basically, is the ruler showing up with my background? Yeah.
Yeah, it is.
So basically, something this size or larger is considered a boulder. So that's like not that big, right? This is not that big. But so in this case, this is a large boulder the size of a large boulder. This is a big sucker. A small boulder could be, you know, this is like, again, this is it. So anything that's this big or bigger is considered a boulder. But then as you go down from that, they get smaller and smaller. And so if you look at this thing about clast size, so it's about the diameter, sort of the largest diameter. You might have seen a lot of these words before. A lot of these words are really just words that you hear, like boulder, cobble, like in a cobblestone street, a pebble, sand, silt, clay. Have any of you not heard these words before? Yeah, so these are really, really common words. But in the context of sedimentary rocks, they actually have very, very specific meanings about size. So again, if a boulder is like this big or smaller, the next size is, so anything that's, so between my index fingers here, anything that's about this size, so between 64 millimeters and 256 millimeters is a cobble. And so like if you think about a cobblestone street, if you've ever been to like a historic place with a cobblestone street, if you thought about the rocks that are there, yeah, they're probably going to be in this range of, you know, anywhere from here, like up to this size, but not below this size. Like up to this size, but not any smaller than this. So the smallest cobble is going to be this size. And the largest is going to be, I have to go back to it now. Cat, do not claw my leg. Ow. The smallest is going to be, or the largest is going to be this size for a cobble. Then a pebble, that's another really specific size. It's anywhere from 2 millimeters, all the way up to 64. So, and beyond that, I can't show you on this ruler because I cannot show you 1/16 of a millimeter, but hopefully just showing you for boulder, cobble, and pebble, how the size gets smaller and smaller, can give you a sense of the kinds of clasts that you're talking about. So by the time you get to sand, that's between 2 millimeters and 1/16 of a millimeter. Then silt is itty bitty teeny weeny, and clay is even itty bitty or teenier weenier. So if you remember last time when I was talking about clay as even if you don't have water in it, it's still clay just based on both what minerals are in it and its size. That's kind of what I was talking about. So in this case, I'm not going to ask you to know, like, I'm not going to ask you like something is 1/32 of a millimeter. What is it? I'm not going to ask you something like that, but I would like you to know the order. Like I'd like you to know that clay is the smallest, then silt, sand, pebble, cobble, boulder. And I would like you to have a sense that like a small boulder the size of a small boulder is not as big as you'd think, but also that things like silt and clay are actually microscopic. Like sand, you can still see individual grains with the naked eye. But for some of these, like you actually need to either have a magnifying glass or a hand lens, or actually this is another reason that geologists lick rocks. Boulder, cobble, pebble, sand, you can tell by looking at it. And if you can't see it, yes, I have licked a rock. In certain field geology classes, you kind of have to. And part of the reason why is being able to tell the difference between sand, silt, and clay. Usually with sand, you can see the grains. With silt, you can't. It tasted like dirt. It did not taste, I mean, it didn't taste bad, but I wouldn't say it tasted good. It tasted like mineral. Like it was, I wasn't like excited about it. But the reason that you lick the rock is not because of how it tastes. It's actually to tell the difference between silt and clay. And silt, if you rub it again, like between, like on your teeth, like if you rub it between your teeth and your tongue, you will be able to feel the individual grains. But with clay, you won't. With clay, you're just going to feel sludge. Whereas silt, you'll feel grains. And so that's why, there are so many memes about geologists licking rocks. Like that's a very, very large subsection of geology memes. I guess I could make a memes section of the forum too and post some of them. I don't know of anyone who's like, I can't wait to lick some rocks. And a lot of people will be like, yeah, we do this just to make people go, wow, that's weird. But the real reason for this, and the reason that I did it was because when I was taking my field mapping class back when I was, actually I took that in grad school, but we were mapping a place that had a whole lot of really amazing looking sedimentary rocks. But we were supposed to, like when you're making a geologic map, which is not something we're really going to talk about in this class, but if it's of interest, geology, I think it's 314 is the class that does that. But it does have a lot of prerequisites. So if you were getting to that point, you might as well pick up a minor or a major. But the reason that I did that is because our teacher wanted us to map, like he said, there are going to be clays, siltstones, and sandstones here, and I want you to tell me which ones are which. And so sometimes you just have to put the dirt in your mouth. Again, it was dirt. It was fine, I guess. I guess there was another time I accidentally got mud in my mouth in the field and it was salty and disgusting, but that's a topic for another time. But anyway, the reason class size is important is not just as identification, but also depending on how big the clasts are, it can actually tell you a lot about what formed them. It can tell you a lot about the weathering and the erosion and the transportation. Because if something is really big, it probably weathered away in something kind of catastrophic. It was probably a big physical weathering kind of situation that probably got detached by either gravity or ice or something very powerful and didn't travel very far, because if it had, it would have gotten broken down smaller. Whereas if you have something like sand or silt or clay, remember that all started as solid rock too. All of these things started as big solid rock. And so if you have something like sand or silt or clay, that means that processes have to have broken it down very small. So a combination of weathering on a very fine scale, but also a transportation process that lasted a long time. Oh, sorry. Yeah. Question?
No, that was an accident.
Okay. Yeah, so also a transportation process that lasted a really long time and bashed it down smaller and smaller. So seeing what you have can tell you a lot about how that rock formed and where it formed. Because I mean, sometimes you can go like, oh yeah, that rock is next to the thing that formed it, and I see that. Like you're gonna find rocks next to a river that obviously formed in a river once you know how rivers form rocks. But if you're looking at really old rocks, like if you're looking at millions of years old rocks as opposed to just thousands of years old rocks, sometimes something that used to be a river or an ocean isn't even slightly close to water anymore. Like most of the desert Southwest used to be in an ocean or a lake, and now it's not. So sometimes you can use these kinds of things to tell what has to have formed that, even though plate tectonics now is completely rearranged what's an ocean and what's a desert and what's what. So does that make sense?
I have
Yeah.
a question.
Go for it.
So if the grains are smaller, that means it stayed longer in the transportation process, right?
Yeah. Generally. It can also mean, though, that the weathering process broke it down really small. So, like, usually if you have, like, extremely small grains like clay, it was probably a chemical weathering that broke things down at the molecular level rather than just by cracking a rock. But you'll usually be able to tell by other factors which one of those was more involved. Does that make sense? Does that answer your question? Oh, okay, cool. All right, anything else about class size before we move on? All right, it'll let me move on. Okay, so the next thing that we look at a lot in looking at clasts is angularity versus sphericity. Is it pointy or is it round? So did any of you ever have like a rock tumbler, like one of those toys where you put rocks in a tube and you tumbled it around, you turned a crank and then they came out sort of rounder and polished? Yeah, I have no idea. So you know of them. I have no idea how much of a thing those still are. You've seen TikToks about it. I guess they are still a thing. Okay. Because I know, like, I mean, I was a kid in the 80s and they were very much like a toy that people commonly got in the 80s before computers. But okay, who would have known rock tumbling TikToks? I mean, I guess it can be soothing. I guess it could be like an ASMR thing. I don't know. But anyway, that same idea of a rock tumbler where you start with something angular and it turns into something rounded, that absolutely happens in nature. And that happens mostly, actually, that is a direct result of the transportation mechanism. So basically, if something just breaks off and doesn't travel very far, it's going to maintain a lot of the just rough edges from where it broke off, or even just the rough edges of the mineral crystals itself. Like if you remember when we were talking about silicate minerals, most of them are very angular, like quartz crystals are hexagonal, feldspars are kind of rhomboids. Crystals are pointy, like by definition. And so even if something just weathers away very slowly, if it doesn't travel very far, you're still going to have the points of those crystals. Or if something physically weathered, you're going to have the sharp edges from where that rock broke. But the longer it travels, the more it gets bashed around against other rocks and bashed around by water and ice, the more it bumps into other clasts. And slowly, or even sometimes not that slowly, it will get rounded out. So basically, if you see angular clasts, didn't travel very far. And if you see rounded clasts, it did. So it's like the difference between putting the rocks in the rock tumbler and cranking it once or twice versus cranking it for 20 minutes. You're going to get something very different looking at the end. And so this example here, so there's two sedimentary rocks here that are very similar in structure. They have a bunch of clasts of different sizes that are held together by a cement that you can see, because these are probably pebble-sized clasts in these cases. And so you can see the clasts here, you can see the cement around them. But in this case, you have really sharp chunks. And in this case, they're a lot more rounded. And so in this case, these things didn't travel very far before they ended up deposited in a pile and lithified, whereas these traveled much further. And so this one on the left, this is called a breccia. This comes from broken in Italian. And you very often get these in places like at the foot of mountains, where like you had just gravity break something off and carry it down, and then it smashes against the ground and piles up and lithifies. Whereas conglomerate is the name for the smoother one. And these are very common around rivers. Like anytime you're gonna have, like that example I was giving of a riverbed eventually turning into a larger sedimentary rock. That's where you get conglomerate, because these clasts are very smooth. You can see they're very rounded. In this case, they've been tumbling along in the river for a while before they ended up deposited on the bank and lithifying into rock. So in this case, like the class size might tell you something, but the class shape is going to tell you something else. So like let's say you had sand-sized grains that were really chunky, then you would go, okay, these probably weathered in a way that was more chemical and ended up kind of chunky. Whereas let's say you had tiny grains that were very rounded, you might go, okay, well, these obviously have transported for a while, so they might have weathered and eroded away in a way as bigger clasts that then got smaller and rounder as they transported. So does that make sense? Any questions about that? And we will come back to this as we talk about different environments where different kinds of sedimentary rocks form. So if you realize you don't got it as much as you think you do right now, it'll come back. But am I good to move on? Cool. All right. Then the last one I'm going to talk about today, before I get into some other stuff, is sorting. And so that's another one that it's exactly what it sounds like, is how, like, are all of the same things together or not? And so in this case, it can be a mixture of different class size, a mixture of different sphericities. It can actually be a mixture of different minerals. Is it a whole bunch of different stuff in one rock, or is it kind of all the same? And so this is also a figure from your book, but just showing like poorly sorted here has a bunch of different clasts. They're different sizes, they're different shapes, all the way to well sorted, where in this case, everything is pretty much the same shape and size. And so some real world examples like this guy, we'd probably still call this a breccia, because these have a lot of different grains of different sizes and they're pretty chunky. Whereas this one, we would call it, this is probably a sandstone. In this case, this is a pretty boring looking gray rock. Like, all rocks are interesting, all rocks tell a story, but if you were gonna like, you would never look at this and go, man, that's the most beautiful rock I've ever seen, because it's a bunch of nondescript gray grains. I'm probably somewhere a sedimentologist is hearing this and is probably gonna come be very upset with me. But you know, everything is the same in this one and everything is different in this one. And so it kind of goes on a scale like these terms, very poorly, moderately, well, and very well, are actually the technical terms for it. They're pretty literal. Like, this is a mess. This is about as organized as it's going to get. But this tells you sort of about, like, did these things come from different places? But a lot more, it tells you about the speed of transportation. So it's not just so much about how fast, but also how variable it is. Because if things are going really fast, then it's going to be able to carry big stuff and small stuff. But if it's going really fast, it's also going to carry all of it. So if it slows down, then it's going to drop the fast stuff before the small stuff. But if it stops, it's going to drop everything. So you might end up with something very poorly sorted, where something was moving very quickly and then it just stops. So like in a case of, say, a flash flood or just a seasonal stream, like a stream where you have, let's say it's only got water in it part of the year, you might have a thing where it's carrying everything and then it dries up and it just drops it. Meanwhile, something that's very well sorted is kind of going to be in a case where actually the transportation speed, it's kind of more consistent. So it can either be a case where like everything is, it's not so much that everything is moving fast versus slow, because you can have a well-sorted rock with very large clasts, but it's kind of, is it changing gradually versus sporadically? So like, let's say you have a river that has a steep slope where it starts and has a more gradual slope as it continues, which is generally what rivers do. You might find well-sorted, really big classed stuff near the top of the river where it's steep enough to carry them for a while, and then eventually it becomes steep enough, not steep, and the big stuff falls out. But then as the slope of the river gets less and less and less, there's going to be points where it can carry only smaller and smaller and smaller things. So as you go along that river, you're going to go from well-sorted big to well-sorted medium to well-sorted small. Because that's consistent about what it's doing. It's just kind of a change in speed over space. Whereas a change in speed over time, in like you're staying in one spot, but things are moving faster or slower at different times, is going to result in different sized clasts being dumped in the same place. So does that make sense? That you get well-sorted stuff where you have a change in speed along a certain distance, and poorly sorted stuff where you have a change in speed in one spot and it's changing over time. And any questions about that? This is also going to come back a lot when we talk about rivers, and also when we talk about the different environments where specific sedimentary rocks form. So those are our major criteria, that and what are the clasts made of, and what is the cement made of. And so knowing those criteria, you can actually break the types of clastic rocks down into relatively few names. So there's still kind of more names here than there were with igneous rocks, and you're not necessarily going to have a like, this has an exact counterpoint that's an exact counterpart. Like with the igneous rocks. But you can still think of it in terms of just, there's certain things that have big clasts, certain things that have medium clasts, certain things that have really little clasts. So if you have really big clasts, it's either going to be conglomerate or breccia. Conglomerate if they're rounded clasts, breccia if they're not. Diamictite is kind of matters less about whether they're rounded or not, but it's basically says there's more mud than there is clast. So in conglomerate and breccia, I mean, you're going to see the cement, but it's usually still going to be more clasts than cement. And in diamictite, it's kind of, there's more, the clasts are usually really big, but there's actually more cement than there is other stuff. Then getting into the medium to coarse, you're talking about sandstones. So sandstones are a whole group of sedimentary rocks, and you mostly classify them by what's in them. And so all of these names, like if it's just quartz, it's quartz sandstone. If it's quartz and feldspar, you call it arkose. If the fragments are of rock rather than of just minerals, like if they're fragments of an igneous rock that you can still like tell are a mixture of minerals, you might call it lithic, because again, lithos is rock. And then if it's sand that also still has enough visible cement, so matrix is another word for cement. Matrix and cement are the same thing. Then you call it wacky. Yes, that's how that's pronounced, wacky. It's real fun to say. But in this case, like I'm not going to ask you too much about the difference between quartz sandstone, arkose, lithic sandstone, or wacky. Whoops, just know that medium to, this table will be, so this table is in your book. And it will be on Canvas once I post these slides after next class. But this is in your book. It's also going to be on the YouTube video of today, and it'll be on Canvas on Monday. And this is going to be one where, like, again, you don't worry too much about the chemical composition stuff. But sort of do know, like, sandstone has medium to coarse. Conglomerate and breccia have really coarse. Siltstone, silt-sized clasts, they're very fine. And then shale or mudstone, if it's even finer. And so the difference here is mudstone is just kind of gonna shatter. And shale is kind of, it's if the sheets, if it forms these sheets, and that kind of has to do with what the specific minerals are in it. Again, we're not going to worry about the specific minerals, but just the structure of the minerals in shale will cause it to have very clear layers. And that's also why shale is a really common rock to find fossils in. But don't worry about, like, why there's a difference here. Just know that shale has sheets and mudstone does not. But these are just distinctions. The first thing to look at is how big are the clasts. And then look at just, like, what are they shaped like? And that's kind of, and then third is look at what are they made of? But yeah, does that make sense? Does anyone have any questions about anything we talked about today? Because that's all I've got for you today. So are we really going to make a meme discussion? I guess I could really, I mean, maybe I'll make it a science meme discussion. We'll see. I'll see how, we'll see how it goes. And I will exercise administrative behavior as necessary. But yeah, we'll see. But anyway, hopefully the discussion board is working. There's another quick quiz that's going to go up for next time right after class is over today. I'm done, so you're welcome to take off. Specifically geologist memes, totally. But you're welcome to take off. If you want to stick around and ask more questions, I will hang out for a few more minutes. And if not, I will, I guess, see you on the forum, but also see you on Monday.
Thank you, Professor.
And have a good week. I mean, I guess it's only Wednesday, but have a good weekend. Have a good one, everyone. Are you all hanging out with questions or taking notes, or what's up? So I think I'm gonna call it a day. So if you do have any questions that you think of or that you were meaning to ask, just feel free to email me at any time and I'll get to you as soon as I can. So have a good one.